I'd like to discuss my views on how we could be using existing data to take better advantage of the data that we already have for modeling. So for those of you who were at the long session last night where people had a chance to present ideas, I showed you this one slide, which I'll briefly go through, in which I was advocating for a marriage of simulation and data. So obviously we need abundant high-quality data, but we also need to take advantage of the data that we already have. And so gaps in data coverage does not mean we have to go out and gather more data, does not only mean we have to go out and gather more data, but we also need to be smarter about using the data that we already have. So to do this, you need good forward and inverse modeling tools, data assimilation, and serious computational resources. So what is motivating my thinking is this graph here that shows you on a logarithmic scale where computing has been going over the last 20 years or so. So it shows the exponential growth in compute power, looking at floating point operations per second, or flops. So we've gone from a gigaflop in 1993 to teraflops in about 2000. We've passed petaflops, and we're moving towards exaflops. We'll reach exaflop capabilities in 2018 or 2020. So the graphs here show you where the number 500 computer in the world is. So this is the fastest machine in the world. This orange line is the number 1 computer in the world. So that's the current fastest machine. And so it's a little bit more jerky because at certain times only one machine can be the fastest system. At the moment, that is Titan. That's a Cray at Oak Ridge, and it's running at more than 20 teraflops. And if you imagine combining all computers in the world together, you would get this blue line. So where does this put you? Well, for example, this Mac laptop here is running at almost 100 gigaflops. So that's almost the fastest machine in the world back in 1993. My iPhone was the number 500 fastest computer in the world back then. So your 2032 laptop is probably going to be running at close to 10 or 20 teraflops, and your iPhone is going to be faster than your simulator was back in 2005. So these are amazing facts. This is happening whether we like it or not, and we really need to tap into this and take advantage of this incredible development. So for example, at the moment, a lot of computers are trying to take advantage of graphics processing units, GPUs. Cray at Oak Ridge, Titan is an example of such a machine that is accelerated by these graphics cards. So you really need to keep up with this trend. It means a large investment in software development and upkeep of software, but the benefits are tremendous. So iPhones are compulsory for most geoscientists because not only was it a supercomputer back in 1993, it's also a seismometer. You can get an app called iSeismometer for your iPhone.
Also got GPS.
And it has GPS. So what are others doing? I just found some examples from the web. This is what the Europeans are doing. This is EPOS, the European Plate Observing System. And if you look at their objectives, number 5 specifically mentions facilities for distributed storage and computing resources for high-performance computing. So they are recognizing that modeling must be an integral aspect of an effort like this. There's Virtue, which is a part of EPOS, and that is specifically focused on developing grid infrastructures, taking advantage of HPC, both for data analysis and for simulation. So this project was recently funded and is growing as we speak. So where are we in the United States in this regard? Of course, simulation has become an integral part of modern geophysics. But as a community, we really are not very well organized when it comes to HPC facilities. So most simulations are currently performed on modest in-house resources. And in my view, our science would benefit from dedicated computer hardware that is optimized for the needs of our community. So the facility that you might imagine would use existing open source community software and a great place to go is CIG, Computational Infrastructure for Geodynamics, where we already have a good collection of such tools. Such a facility could act as a platform for research computing development. You need access to these kinds of resources to develop the tools. It would provide human resources in the form of dedicated software and system engineers. And believe me, to take advantage of these systems, you really need excellent people from computational science and engineering and system administrators to make all of this work for you. So we really need to engage that community. The hardware and the access policies on a system like this should reflect the way we do research. So also with an eye towards our education and training. And a lot of the current systems are not set up for our types of problems. And a little bit later in the talk, I'll give you an example of why current scheduling policies, for example, on large systems are not favorable for the kind of science that we tend to like to do. And I'm not necessarily talking about a facility that is a bricks and mortars facility. It could easily be located at an existing HPC center and involve a collaboration with that center. So a little bit more about what facility we might envision. Of course, it needs hardware, but again, it can be located at a number of existing centers. A really important aspect of this is that it needs to involve human resources so that you get what Tom Jordan has called an HPC ecosystem. It's really important to have the human component in place so that we have people that we can go to, that we know, that understand what it is that we like to do, and that we can directly interact with, and whose job it is to make sure that we are successful on these systems. So we need software engineers for code development and optimization. We need system administrators that work directly with us and for us. We also typically do simulations that may harness perhaps 100 or a few thousand cores, but not necessarily hundreds of thousands of cores. So these systems these days have hundreds of thousands of cores. Titan has 300,000 compute cores. The kinds of simulations we do typically don't harness the entire system for a single simulation. Sometimes they do. But often what we like to do instead is do many smaller forward simulations to do ensemble type simulations or inverse problems. We also need to be able to do massive data assimilation, so we need data very close to computing. And in this regard, IRIS is already engaging Livermore, for example, to look at mirroring the IRIS database. So as I mentioned, we typically do hundreds of simultaneous simulations during forward and inverse modeling. We also need fast remote data pre- and post-processing capabilities. So in the example I will show you, which is a tomographic inversion, there's a lot of pre-processing and post-processing that needs to happen. That's non-trivial on very large parallel platforms. And for example, the existing data formats that we use are completely unsuitable. So we need to start thinking about how we can change our data formats to take advantage of these kinds of systems and tools. A lot of what we do needs to be virtualized. So you're using this large remote system, say this Cray Titan at Oak Ridge, and you want to see what you are doing. So you need to be able to virtualize, for example, a line search or the smoothing of a model or whatever have you. And again, that's not a trivial affair. For some applications, we'd like to be able to do near real-time simulations, for example, to simulate earthquakes as they happen. And there are tools at CIG that enable on-demand simulations, where as a user you can come in through a website and request a simulation online. And of course, there has to be a really significant component of education, outreach, and training. And in this regard, these collaborations with these compute centers are really fabulous, because I think our students, our postdocs, we as faculty, we can learn a lot from interacting with these centers. Okay, so I'll give you a few examples of how in my research we use these tools for imaging. So this is an example of data assimilation looking at imaging Europe. This is the work of Jeroen, a graduate student at Princeton. So what Jeroen did is he collected about 190 earthquakes, and you can see here the beach balls are all the earthquakes along the mid-Atlantic ridge and through the Mediterranean, recorded by about 745 stations. A lot of those are temporary arrays, but Many of them also are permanent stations. So I'm going to show you how, over the course of 30 tomographic iterations, updating the model along the way, we can retrieve structure in Western Europe. So in this particular inversion, we're assimilating about 123,000 measurements, by which I mean windows in the seismogram that we're trying to fit, using about 2.3 million CPU core hours, which, by the way, is not a very large number these days. So to illustrate how this works and to highlight some of the challenges, this is the workflow that goes with an inversion like this. So starting at the top, we have 190 earthquakes. And the first thing we do is we do an initial source inversion for all of these earthquakes. So all the red boxes show you where we are doing computation and where we are harnessing these computational resources. So once you have all your simulations, your synthetic seismograms, and you have the data, you can compare the observed and simulated seismograms and make measurements. And so this is where the data are being assimilated. Then we construct what we call the adjoint sources, which is where the data gets assimilated. And then we calculate the gradient of our misfit function to do the optimization. And again, that's a massive calculation. When you're done, you sum the gradients, one gradient for each earthquake, and then you might do some preconditioning and smoothing as part of the post-processing process. You determine a step length, you update your model, and you repeat. So there's virtualization in the green boxes when you do the pre-processing and the post-processing, and we iterate. Typically, we use some sort of a quasi-Newton method, perhaps LBFGS. So here's one place where current data formats are inadequate. This step of comparing observed and simulated data, the way we currently deal with data, where we have one time series is one file, becomes completely debilitating on a large system such as this. So you need to combine information so that you say have one file for the observed data, another file for all the synthetic data, a bit like a SegWi format, and then do the processing in parallel. And so there are more modern formats for this purpose. NetCDF, HDF5 are example of these kinds of file formats. What we are using is called ADIOS. It's a file format that is being developed at Oak Ridge National Laboratory. And so this is an illustration of where our current practices fail. And if we want to take advantage of these resources, changes will have to be made. The same thing is true in the post-processing. There you have large volumes of data. In our case, the gradients are volumetric data. And they need to be stored in a format that is amenable for parallel processing, for example, the preconditioning and smoothing. And that, again, requires a different data format. So this is just to illustrate what the ultimate goal is in these inversions. So imagine you have a little earthquake on the ridge here near Iceland, recorded in Kiev. What you're seeing from the top to the bottom are the three component seismograms, the vertical, the radial, and the transverse. In black are the data, and in red are the synthetics for our starting model. The panels show you places in which the data and the synthetics are sufficiently close that we're making measurements. And so these are the measurements that get assimilated. So you can see, there's no pointer in this, but the radio wave on the vertical and the radial is not fit very well by the starting model, and so it's currently not selected for inversion. But the love wave on the transverse in the bottom is already matched reasonably well, and so we're making a measurement there. So the goal is to fit frequency-dependent phase and amplitude anomalies in targeted windows. So this is how we go about doing this inversion. And of course, the ultimate goal is to fit entire seismograms. But rather than assimilating these seismograms all together, all at the same time, like you might do in the industry, we do it iteratively. And as the inversion proceeds, we pick up more and more windows, again, hoping to ultimately fit entire records. So this window selection is done using this package called FlexWin that was developed by Alessia Maggi. So here's an example of how the model evolves. This is at a depth of 75 kilometers. This is the starting model. So you see relative variations in shear wave speed at a level of about plus or minus 3%. In blue there you see the Eastern European platform, which is very fast, presumably cold. And in red, you see the slower areas, for example, the Western Mediterranean, which opened up in the last 30 million years or so ago. You see Turkey and you see Iceland. And so this is a typical global model, wavelengths on the order of 5,000 to 10,000 kilometers. So after 30 iterations, this is Jeroen's model EU30. And so you see all these small-scale features that emerge from this background. A lot of them have geophysical or geological relevance, like this is the Bohemian Massif in the Czech Republic, Slovakian volcanic field, Middle Hungarian Line, a geological feature in Hungary. This is the Pannonian Basin. It also opened up in the last 40 million years or so. This sharp contrast is the Tornquist-Tessera suture zone. This is the Massif Central in southern France, Brittany, Eifel, the Eifel hotspot and the Rhine-Graben. This is the Central Graben in the North Sea, and this is the Harz. So the point really here is just to show how using these iterative inversions, these much smaller scale details can be resolved from this background model. And after you've done these 30 iterations, this set of seismograms that I showed you previously might look like this. So at this point, we're seeing a better fit to the radii wave. We see that the body waves overall are fit better, and we also see a slight improvement in the fit to the love wave. So that's the goal of these types of inversions. I also wanted to say a little bit more about how you can take these types of approaches further. So we've just recently started to look at anisotropy, so a directional dependence of the wave speed, and that's readily accommodated in these types of adjoint methods. So a couple of slides just to illustrate how that works. This is anisotropy at a depth of 125 kilometers. The red lines denote the direction of the anisotropy, and the length, their length denotes the magnitude. So you see what people have seen before along the ridge, that the fast direction is perpendicular to the spreading direction. But you see all this beautiful tectonics, the escaped tectonics in Turkey, for example. You can see how that Tornquist-Tessera suture zone is, now I never know which screen to point at, but you can see how that is recognized by the alignment, by the direction of the fast axis. At 50 kilometers, so shallower depths, maybe seeing deep crustal anisotropy, you see the signal is weaker. You still see the spreading perpendicular to the ridge, but you also see interesting features in, say, here underneath the Baltic shield, and that's a crustal flow. So if we investigate that a little bit further, looking at some profiles here. So this first profile 1 is on in the Atlantic, and what I'm showing you at the top is the shear wave speed, Vs, and at the bottom is the strength of the anisotropy. So G0 is the magnitude of the anisotropy, and so you can see in this case that the anisotropy peaks at about 75 kilometers depth. So here, if you think about a strength profile for the oceanic lithosphere, we're here below in this ductile region where things can get aligned. This is another oceanic profile here, number 2. Again, you see the nice reduction in shear wave speed in the asthenosphere and the alignment, the strong anisotropy at about 100 kilometers here. This is in the Western Mediterranean, similar. This is in the Pannonian Basin, deeper anisotropy. And now things get interesting here in Turkey. You see that if we look at the strength of anisotropy, you see that there's a peak here. The gray box denotes the crustal thickness here. So you see here that in the deep crust, you see crustal flow and stronger anisotropy, and then again a second peak for the asthenospheric flow. So you might think about this kind of a strength profile where we have the strong crust and then the lithosphere and the ductile regions that accommodate the deformation. So some more profiles here underneath the stable continents, and we continue to see this crustal flow signature in that case. And you also see how now the shear wave speeds really pick up, increase underneath these stable platforms. So where would we like to take these things looking forward? Well, the goal on Titan for us is to start looking at global inversions. And really here, we should be using all the data that are available. So at the moment, we're just looking at a small subset of events, about 250 earthquakes. But since 1999, more than 6,000 earthquakes with magnitudes in the range of 5.5 to 7 have been very nicely recorded by the global network. So we should be assimilating all of that data. It's sitting right there. What is holding us back? And what's holding us back is just sheer processing power and the tools we have available to analyze that volume of data. But potentially, we would easily be looking at assimilating some 50 million measurements or something of that order. So again, the goal is to go towards full waveform inversion. And this is just illustrating how much information is already in these global seismograms. So this is an earthquake underneath Argentina. It's a deep 6.3 event. The bandpass is 17 seconds to 60 seconds. So this is work by Ebru Bozdag. She's a postdoc at Princeton looking at these global inversions. So here this is arranged by distance, so from 54 to 144, initially looking at the P. Again, in black are the data, and in red are 3D simulations for S362 ANI, so one of the current global models for this earthquake. And what is stunning is how much agreement there already is between these simulations and these observations. So you really want to be assimilating all of this information to constrain your Earth model. You don't want to just focus on P or PKP or SCS or whatever your favorite phase is. You want to try and take advantage of all this detailed information in these records. So this is what we hope to do on Titan. So as I said, this is the #1 supercomputer as of just a few months ago, and this is what it looks like. So it has a peak performance that exceeds 20 petaflops, almost 300,000 AMD opterons, and each node, there are 18,000 nodes, each node has one graphics card, one NVIDIA graphics card in it to accelerate the simulations. So we have 100 million core hours on this system. Remember, the European inversion took 2.3 million core hours. So this is a lot of core hours to see what we can do on this type of hardware. So I want to just end with a few slides thinking about potential partnerships. And the industry is an obvious candidate, as are the national labs. So we've already heard several times the industry collects, processes, and utilizes vast volumes of 3D and 4D data sets. We looked at time-lapse migration. So we should explore that potential collaborations that involve data sets like that. So I mentioned our challenges in I/O, dealing with large volumes of files. So deciding what data formats to use for fast parallel I/O is something that is an issue also in the industry. We should not go this alone. We should engage them while we are trying to resolve these kinds of difficulties. The industry is also working on cheap, abundant sensors. They are interested in lots of things, not just imaging petroleum reservoirs. They're interested in volcano monitoring, of course, time-lapse migration, but they even look at things like dike stability, where they look at slow creep of dikes. This is Shell in the Netherlands, where you have some dikes to worry about. They also, of course, on the science side of things, are quite far along in terms of what they call full waveform inversion and imaging, and there's a lot we can learn from them in this regard. The approaches they use, the workflows that are involved are very similar, and we should clearly be partnering with them to deal with these kinds of issues. I showed you one example of an HPC workflow for our inversions. Those workflows are very similar to what people encounter in the industry. And in this regard, collaborating with, say, the national labs is going to be very, very productive for us. So this is just one illustration of what Shell does when it comes to sensors. So this is just from the Shell website. And this little box here illustrates how Shell has developed this very relatively cheap sensor in collaboration with HP. So this is something that clearly is of great interest to them. I saw this sensor. It's about $100. I don't know. I think we'd be crazy to try and reinvent the wheel, but we should really be talking to these guys and find out how we might be able to join our efforts. So let me just summarize some of my thoughts for this presentation. So first of all, I think we should not just blindly focus on more data, but we should also focus on harnessing the data that we already have. To do that, we need simulation, modeling, and massive assimilation of data in these calculations. I think as a solid earth science community, we need a dedicated computational facility. And a facility like this should involve hardware, software, and wetware. It should be an HPC ecosystem. When we do this, or while we do this, we should keep in mind that there are lots of opportunities for potential partnerships. There are partnerships within existing solid earth organizations. So we have IRIS, CIG, SCEC, CIDER, EarthScope. Clearly, none of these entities should go this alone. We should do this in close collaboration. And I should say there is an effort underway. We've had a number of workshops to discuss these ideas. I think within NSF, there should be opportunities, for example, between OCI and EAR, but also with other agencies. So many of the national labs are run by DOE, but often there are both NSF systems and DOE systems sitting at these labs, for example, at Oak Ridge. So I think there may well be opportunities for collaborations between DOE and NSF. I also think we should really seriously look at collaborations with the petroleum industry for practical reasons and for scientific reasons. And we should work in close collaboration with the national labs because they have a lot to offer. A lot of these facilities are located there. And a number of these labs, in particular Oak Ridge, now have fabulous collaborative programs where when you win an allocation, they assign liaisons to you whose job it is to make sure that you are successful. So it's not just giving you an account and saying, off you go, but they really work very closely with you in what I think is a very good partnership. And if I look at how my students and postdocs are participating in this project, they really enjoy this. So I think there are tremendous opportunities for working much more closely with these labs. So with that, thank you.